I've got a ton of material to cover today. You're going to see skipped slides because I always have too many things in my slides to cover, so I often pick and choose as I go. But broadly, I'm interested in binary star astrophysics, and so I always like to start my talks off talking about why should you care about binary stars. And so one of the things I learned as I learned more about binaries is I kind of had this realization that, orbital motion has been one of the most important physical observables just kind of in human history in a lot of ways. So this is a DSS image of the double star Castor, which, by the way, is actually a sextuple system, but they didn't realize it until much later. And it was William Herschel was looking at this system in the early 1800s and was a little puzzled because he looked at an old drawing of the system and had noticed that the angle between the two stars was different 80 years before. And it was that caused him to realize that, hey, these were bound and orbiting each other due to Kepler's laws. That might sound pretty mundane to us, right? Okay, it's a binary star and orbiting. But it was a really profound thing because it was the first time someone realized that one of these laws of science we had come up with, the law of physics, applied outside of the solar system. If you kind of look at it, the history of how science developed, there were a lot of these realizations where people were very narrow-minded and thought the Earth was the center of the solar system or the universe. And they started to expand and realize that we were just one speck in all of this. And this was really the big leap to realize these rules were coming up with work everywhere. There was another really important example of orbital motion shedding light on some of these rules. The precession of Mercury around the sun was one of the first important tests of general relativity. Another type of orbital motion, the shrinking of the Hulse-Taylor pulsar's orbit almost a century later, was another very important test of general relativity, showing orbital shrinking due to the loss of angular momentum through gravitational radiation. The imprints left in space-time by the orbital motion of two black holes coalescing was another yet very important example of how orbital motion shed even further light on general relativity. In fact, if you think about most of what we know about gravity comes from orbital motion, perhaps not by accident. The orbits of the S stars around the center of our galaxy are what revealed the presence of a supermassive black hole there. And even the tiny wobbles of the orbit of a star, 51 Peg, revealed the existence of planets outside the solar system. So just to give you context, like there's a lot that comes out of studying things orbiting each other. Also, I want to note that about half of all stars are in binaries, including almost all massive stars, which if you care about compact objects are the progenitors of those. You might go, well, Kevin, I know how stars work. Like, why do I care if the star is in a binary or not? Well, I'm going to tell you a story about a special star system called Algol. This actually means demon in ancient Arabic, apparently. It perhaps meant demon because the star does a weird thing. It dims by a little bit every couple days and then gets brighter again. And people didn't really understand why that was. That's because they didn't have tests to show a beautiful light curve of an eclipsing binary that this is, with an orbital period of 2.867 days. But why is Algol so special? Well, there's this thing called the Algol paradox you may have heard of, and let me explain what that is. So in Algol, you have this star that's overflowing its Roche lobe, so it's dumping matter onto another star that it's in a companion orbit with. And the reason this star is dumping matter onto the other star is it tried to become a red giant. But this other star had something to say about it. It said, 2.867 days, you're not going to fit a giant into an orbit that short. So I'm going to start consuming matter instead. But the curious thing is we can measure the masses in the system very precisely because it's an eclipsing binary that's also a double line spectroscopic binary. And we find that this donor star is about 0.8 solar masses. And the star that's eating it is 3.7 solar masses. And now you should think back to your stars class and go, wait a minute, something's a little fishy here because I know more massive stars spend less time on the main sequence. So how did the 0.8 solar mass star try to become a giant before the 3.7 solar mass star? Well, the answer is that binary evolution completely changes the picture of what you learned in single star evolution. So it gives you end products that you could never have gotten if you just allowed stars to evolve in isolation. And in this example, the star that's now 0.8 solar masses probably started out as the more massive one and lost most of its mass to the other star through mass transfer. And that's why we have this weird paradox of the low mass star being the one trying to be a giant first. Okay, so I'm going to talk about a few of my favorite questions that binaries are the key to answering. This is by no means an exhaustive list, and I'm not even going to get time to go through the entire list in this talk, but just to give you an idea of some of the things I get excited about. One is, how do binaries change their orbital periods? That's a really broad problem. One of the core questions related to that is we see all these merging black holes. How the heck do black holes get into orbits close enough to each other to merge within a Hubble time? Because they come from really massive stars that have a hard time squeezing into short orbits like that. I'm going to give a lot of other context where this is an important question and how I sort of seek to answer it. Where do these really important standard candles called type 1a supernovae come from, which you may have heard of because they were used in sort of a Nobel Prize winning discovery of the accelerating expansion of the universe? The embarrassing secret in the white dwarf community, at least, is that we still have no clue exactly how they work or why they follow this Phillips relation that seems to be so powerful. How massive can a neutron star get before it collapses into a black hole? You can also use binary systems, these special things called spider binaries, to probe that physics. And how do stellar mass black holes form? And I'll get to that one in the end. That's something I haven't told anyone about today. So all of you who talk to me, there's new stuff coming. Okay, I'm going to start with the double white dwarfs, though, because that's what I did my PhD on. And so they're very near and dear to my heart. It's a really exciting time to be working on double white dwarfs right now. And the reason for that is there's currently a space-based gravitational wave detector called the Laser Interferometer Space Antenna that's being led by ESA, which, given the current funding climate, I'm very happy about. It's a constellation of 3 satellites that will be in a trailing orbit, following the Earth around and rotating, performing time delay interferometry. And it's sensitive to gravitational waves in the millihertz regime, so much lower frequency than what we see with the ground-based detectors. I want to highlight it's a complementary detector. Like LISA is not a better LIGO or Cosmic Explorer, and LIGO and Cosmic Explorer are not a better version of LISA. They look at different things, and they're really complementary to each other. So different frequency regimes. So here on the x-axis, you have the gravitational wave frequency. The y-axis is the characteristic strain, which is amplitude of the gravitational wave. And so ground-based detectors work on detecting gravitational waves at kind of the 100 hertz level. So they're perfect for merging stellar mass black holes and neutron stars. LISA is going to operate in this intermediate frequency regime of about 10 to the minus 2 hertz as its peak sensitivity. And I'm not going to list off all of the different astrophysical objects on this plot, just to show there's a lot in this space that you can study, and you really need to probe the different frequency regimes to access all of this astrophysics. The same way we do in the electromagnetic. Like, it would suck if we could only work in gamma rays, or only work in radio, or only optical. So much comes out of multi-wavelength studies. I don't have time to talk about all of it, so I'm going to talk about my favorite stuff, which are the resolvable and unresolvable galactic binaries in the millihertz. And let me explain why they're my favorite. So millihertz gravitational waves are really cool because currently with high frequency gravitational waves, all the sources we see have distances measured in gigaparsecs. They're really far away. Millihertz gravitational waves are going to reveal thousands of sources in the Milky Way galaxy itself. And there's an important difference between these sources and the ones we currently see. We currently see transients. You see the gravitational wave and it's gone. These are going to stick around for hundreds of thousands of years. They're persistent sources of gravitational waves. And so you can build up signal to noise ratio, do all sorts of things with them, time them over the years and watch how they evolve and so on. And the amazing part is almost all of them are going to be so-called multi-messenger sources because almost all of them will also be emitting photons, electromagnetic waves, simultaneously with those gravitational waves. And there's all sorts of fun stuff you can do by analyzing those at the same time as each other. So what are these sources? Well, the vast majority of them are white dwarfs. And so white dwarfs are really special for a few reasons. One of them is we think we understand their equation of state really well. And what that means is we can make plots like this. Like I can show you, this is the radius you expect a white dwarf to be as a function of its mass and solar masses. The heavier it gets, the smaller its radius gets as gravity crushes it in. If you're someone who works on binaries, this bottom plot is much more natural. This shows you the density of a white dwarf as a function of its mass. As you make it more massive, it gets more dense because it's getting crushed and wants to try to collapse into a neutron star. Why is this important if you work on binaries? Well, before you fall asleep for the rest of the talk, if there's one thing that's worth remembering from today, it's this equation. This equation tells you that the period of Roche-Loeb overflow in a binary, what does that mean? It means that something starts leaking matter through the Lagrange point onto the other object. What it really means is this is the shortest orbit something can fit into in units of days. That is given by 0.43 divided by the square root of that object's density in grams per centimeter cubed. You can plug in the number for the sun. The sun's about 1.5 grams per centimeter cubed, so just a tad denser than water, and you find the sun can squeeze into an 8-hour orbit. Remarkably, the sun does not care if it's orbiting a 10 solar mass black hole or a 100 solar mass black hole or a 1 solar mass white dwarf. This does not care about the mass of the accretor almost at all. It's extremely insensitive to the mass ratio. What it's saying is the orbit you can fit into is just a function of your density. And the lower density object is what's going to set the limit on how short the orbital period of a binary gets. Really simple equation. You can plug in things like the Earth's density, you get 4 hours and so on. Why is that so useful? Well, now I can convert this bottom plot of density versus mass and turn it into a characteristic orbital period for which electron degenerate matter will overflow its Roche-Loeb. And it's pretty easy to read off why LISA is a perfect tool for studying white dwarfs, because 2 divided by the orbital period is the gravitational wave frequency. So that's directly how from the equation of state you can understand why white dwarfs fall right in the middle of the LISA band at their most extreme periods. So now I'm going to walk you through why I actually like these things so much, and I'm going to use my very favorite astrophysical object to walk you through it and just talk about all the things we can measure with these. So my definition of what I mean by multi-messenger astronomy. So the source is my favorite because I published my first paper on it. It's a binary that has an orbital period of 6.91 minutes and undergoes this really deep eclipse every 6.91 minutes. And I've highlighted some text here showing that this is so loud in millihertz gravitational waves that we expect LISA to detect it within the first week of turning on. We're basically saying, LISA, if you don't see it, you're not operating correctly. It's the nice advantage of knowing ahead of time that the source exists as like a sanity check. It's like telling someone if you point your telescope at the moon and don't see the moon, you should check your camera, right? Make sure the lens cap is removed. So what do you get from these? Well, you get gravitational waves, right? This periodic deformation in space-time. And the amplitude of those gravitational waves is given by a prefactor times this inclination dependence, so the orientation of the binary from our perspective. And that prefactors relate to the masses of the things in the binary. This is like a reduced mass called the chirp mass. It scales as the distance to it. The further you put it away, the weaker the gravitational wave amplitude gets, and the gravitational wave frequency. Interestingly, there's a second polarization of gravitational waves where space-time wobbles in like a 45-degree angle compared to the first polarization. And it has the same amplitude prefactor, but a different inclination dependence. And so if you measure both of those, you can take the ratio and those amplitude prefactors cancel, and you get a really clean estimate of the orientation of the binary from our perspective. Normally, this is hard to measure because you need to sample the gravitational waves from a lot of different angles to do this. And for LIGO, for example, that's difficult because if they disappear in a blip, you don't really have much time to check what they look like from different angles. But with LISA, these are hanging around for hundreds of thousands of years. And so the constellation of satellites keeps orbiting around and building up information about what the gravitational waves look like from different perspectives. And so it measures both of these pretty well. So that's what you get out of the gravitational waves. Now let me talk about the electromagnetic waves. So if you watch the total flux out of one of these systems in electromagnetic light over time, you can see this is real data of the object. It's a high-speed movie taken with a 10-meter class telescope. You'll notice it disappear periodically. Why is that happening? It's because one of the objects in this binary is blocking our view to the other one that's contributing most of the light. What you can do then is you can take these photons and split them up by energy and turn it into a spectrum that's also a movie. And you can watch these hydrogen lines in the spectrum undergo Doppler shifts periodically of thousands of kilometers per second and measure things like the velocities of the components using those lines. And to me, the ultimate multi-messenger astronomy is imagine getting all of this simultaneously and everything you can do with that, because the light curve and this are tracking the orbital motion very precisely. And of course, the gravitational waves are also locked to the orbital motion. So it's analyzing all of these signals in tandem is my version of multi-messenger astronomy. Let me show you how much you can get just out of that signal, just the electromagnetic flux as a function of time. And to do this, I'm going to guide you with this little movie of the system so that you can actually visualize what I'm talking about. So the first thing you might notice is there's this sinusoidal modulation out of eclipse. What is that coming from? It's coming from a day-night cycle on this blue-white dwarf here that's being heavily illuminated by this yellow one. It's kind of like the sun irradiates the surface of the Earth or the moon and you get a day-night cycle. Same thing here. So as the day side rotates into view, you go to the maximum. As it rotates out of view and you see the night side, you get to the minimum. At the peak of the day side, you get a shallow secondary eclipse as this yellow-white dwarf blocks kind of the noon point on the blue-white dwarf. And so you can kind of infer its radius from that. But the real star of the show is this deep primary eclipse. And so let me explain how powerful this is. When you see waveforms and things like LIGO, you have to run a bunch of analysis to figure out what's going on, right? If I see one of these in Rubin data, for example, or ZTF data, without even following it up or doing anything other than looking at the fact that there's this eclipse, I can tell you all of the following things. The inclination's close to 90. I wouldn't be getting an eclipse if I didn't have that. And if you model it, you can pin it down to better than 1/10 of a degree. I can say, wait, object number one, the yellow one, the thing being blocked here, must be much hotter than object number two because that eclipse is really deep. And so it's contributing most of the electromagnetic flux. Sigma t to the fourth tells me that means t must be really big. By the way, that's an exclusively electromagnetic observable. You're not going to get temperatures from the gravitational wave component here. But you can also say, wait, the eclipse goes all the way down to 0. That means cool object number 2 must be bigger than object number 1 because it's able to completely block it. And then you can even break out the white dwarf equation of state and go, wait, a small hot white dwarf is always going to be more massive than a cool big puffy white dwarf just based on how white dwarfs work in their equation of state. And so just by looking at the light curve without doing anything further, you already have a pretty solid picture of what's going on in the system. Yes?
Probably you answered it in the following slide. What about the lensing?
There is potentially lensing, not in this system though, because they're too close to each other. So yeah, the separation is just too small for a significant self-lensing signal. But yes, there are white dwarfs where you see that too, and it actually dilutes the amplitude of the eclipse. You can even infer the mass ratio from this light curve, because if you look at this blue-white dwarf, you'll notice it's being tidally deformed into this teardrop shape, and that geometry imprints itself in the light curve and tells you something about the shape of the Roche lobe, which is a function of the mass ratio. So this is all just coming from that light curve. You might even be worried and say, wait, if this is being deformed, could it be accreting? And well, if you're worried about that, what do? You point X-ray telescopes at it and you check, do I have any X-ray photons from it? And in this system, we don't see any. This is with XMM, a 30 kilosecond observation that just so happened to be taken in the field, not by us, but by someone else. And that lets you put really stringent limits on possible mass transfer. I'll show later there are systems where you get loads of X-rays because they are mass transferring. You can go even further and say, okay, let's take this eclipse, which is a really precise clock. And if the orbit were not changing its period at all, we'd expect that eclipse to always show up exactly every 6.91 minutes. But what we find if we try to use it as a clock is the eclipse starts happening sooner and sooner and sooner than you'd expect for a perfect clock. And why is that? It's because the clock is speeding up. The orbit's decaying due to the emission of gravitational waves. This is exactly the same kind of plot as was done for the Hulse-Taylor pulsar, except the decay rate's more than an order of magnitude faster here because the orbital period's so much shorter. If you assume the decay is due to pure GR, there's a relationship between the orbital decay rate and the gravitational wave frequency and the chirp mass. If you assume the decay rate's due to pure GR, you measure this, and that's a really complement measurement to the amplitude we got from the gravitational waves earlier, because those also depend on the chirp mass in the same way, the gravitational wave frequency, but they have the extra parameter of the distance. So if I get chirp mass and gravitational wave frequency for free, that means I can now pull distance out of the gravitational wave amplitude. I'm not even going to talk about the fact that you can also measure parallaxes to these using their optical counterparts.
Sorry, what is the y-axis?
This is eclipse drift time. So the idea is if it were a perfect clock, it would just stay at 0. And this is telling you how many seconds earlier the eclipse is happening compared to what a perfect clock would have predicted at that time. And you'll notice this is bigger than the total orbital period by like a factor of 10, right? What that means is it's like it skipped 10's full orbital cycles over the course of 10 years. So it's like a clock that's running too fast and is literally skipping entire days or something, where a day here is 7 minutes. One nice thing about this expression is if you take a second derivative of it, it's got a lot of stuff going on, but if you take a second derivative, it turns into this really easy equation that says the second derivative is just 11/3 times the first derivative divided by the gravitational wave frequency. What you do is you then follow and time that eclipse for longer and longer, and you measure that second derivative. And you check, is it an 11/3 out front or not? And if it's not, it tells you there's more than just GR at work here. This is all just coming from watching that eclipse so far. We haven't even talked about the spectra and all the other things. But let's do even more with the eclipse. You could go to shorter wavelengths and look at how it behaves. And the eclipse looks pretty similar, but you notice this amplitude of irradiation gets smaller. That's telling you something about how the electromagnetic flux is getting reprocessed off of the cooler white dwarf. If you want to go to shorter wavelengths, unfortunately, there's this pesky thing called the ozone layer that for whatever reason we decided to stop getting rid of. But fortunately, there's this really nice telescope called Hubble that can look at ultraviolet photons. And so if you look at this with Hubble, this is what you see. Suddenly, that amplitude of modulation goes to 0. None of the light is being reprocessed in the ultraviolet. You're only seeing the hot white dwarf now. But the eclipse looks very, very similar. But the really cool thing you can do with Hubble is the following. If you try to take spectra from the ground, I showed you see those Doppler shifts in those lines, right? The problem is the lines are a mix of absorption lines from this hot white dwarf and this emission from the day side of the other white dwarf. It's a mess trying to measure precise velocities out of it, even though you can clearly see they move through each other. You try to measure velocities and you get very poor constraints out of this. But Hubble is only seeing light from one of the white dwarfs, the hot white dwarf. And in the UV, you get very narrow metal lines that you don't in the optical. And so you're able to cleanly pull out lines with the Hubble data by splitting those photons according to energy, making spectra, and measure a really precise motion of the white dwarf and get a really clean radial velocity. You combine that with everything you just did with the light curve and you get a chirp mass for the system. And what you can do is you can then plot, this is what the decay rate in blue is what we predict should be if it were just GR. The red is our measured decay rate. By the way, there are error bars there. It's just that it's measured to a part in 5,000, so your eyes can't resolve the error bars. This is more than a 3 sigma discrepancy. The system is decaying faster than what just general relativity would give you, which is perhaps not a surprise because we expect tides to be acting in this system. Speaking of tides, one of the predictions from tides should be that this blue white dwarf should be heated by tidal dissipation. But it'd be really nice to know how warm it is. Unfortunately, the way you'd measure that is you measure the bottom of this eclipse, but you notice that goes to 0 here in the ultraviolet and the optical. So what do? You go to redder wavelengths. Okay, you see the modulation's getting bigger, but the eclipse is still pretty low, and so you keep going redder and redder. And then you run into this problem of the atmosphere just prevents you from going much redder on the ground. But the eclipse is still going to 0. So what do you do when you want to study something really cool? Use this very cool telescope called JWST, which is designed to do exactly that. And when you point JWST at this, what you see is suddenly you have plenty of signal in the eclipse. And so you can actually measure that temperature, which is about 6,000 degrees. State-of-the-art tide models tell you that this should be about 15,000 degrees. That might sound like a factor of 3 difference to you, but remember, a 15,000 Kelvin black body is radiating a whole lot more energy than a 6,000 Kelvin black body. So that's actually a huge discrepancy. You can even make even longer wavelengths. And so now this plot is a total mess because I put way too much data here. So I'm going to clean it up. And to show you, you see this puzzling thing when you clean it up and look at only the optical and the JW data, and that you might notice the optical is very clean and symmetric. But the JW data has this weird bump, and it's like, what's going on there? So it turns out this bump, we think, is actually because there are winds on that cooler white dwarf trying to transport heat around to its night side because it's being blasted by this 50,000 Kelvin companion. And so you're seeing that. So this is my version of multi-messenger astronomy. This is a gravitational wave source, but look at everything you can do with it. Okay, so you might go, Kevin, you spend a lot of telescope time on that. As cool as that sounds, like, is it really worth Hubble and JWST and all of this? So let me try and make a case of why these things are so interesting for broader picture stuff. And I'm not going to be able to talk about it all, but I want to mention they teach us a lot about how binaries change their orbital periods. So one of the main ways we think these things form is through something called common envelope evolution. And in a nutshell, the important things to measure if you want to understand common envelope evolution is we like to understand its efficiency, like how efficiently does energy get deposited into removing this envelope. And what you need to know is the initial orbital period before common envelope and the final orbital period after common envelope, because that tells you the delta orbital period and the associated delta energy associated with it. Problem is if I give you 2 black holes or 2 neutron stars, it's really hard to tell, like, when did they come out of common envelope? But white dwarfs are not fusing, and they're at some finite temperature. And that temperature is a really good diagnostic of how old they are. So if I tell you the temperature of a white dwarf, I can run time backwards and tell you when that white dwarf formed out of common envelope. And I can go even further and say, if I know the helium core mass of a white dwarf, I even know the orbital period that its progenitor initially had a mass transfer event at. And so I can give you both the pre and post orbital periods for the common envelope. And Jim Fuller and his student have been using all of my discoveries to do exactly this. So constraining common envelope evolution with these systems. They can tell you about how binaries change their orbital period in a whole different way. So I discovered this system where there was a star being eaten by a white dwarf. But the puzzling thing is I took a spectrum of the star and it was an F star. But it was in a 51-minute orbit. And remember the rule I told you earlier is the sun can fit into an 8-hour orbit, and F star has no business being in a 51-minute orbit. And the reason is it may look like an F star, but it's only 0.1 solar masses. And what had happened is it was originally an F star. It ran into a white dwarf, and the white dwarf just gradually ate it over gigayears and whittled away its atmosphere. And now all you're seeing is the little remnant of a core that's there. So this shrank its orbital period into the gravitational wave band, but not with common envelope, just with stable mass transfer. So there's another example of how we learn about how systems change their orbital periods from these. One of the predictions of this is that they should spiral back out as their equation of state changes. They can actually grow in orbital period. And a student working with me, Johin Chakraborty, has been studying the most extreme white dwarfs known, under 10-minute orbital periods, two systems we discovered that are accreting with a disk. And he timed them, and for one of them, he saw this concave down timing solution, kind of like what I showed you earlier with the orbital decay. It means the clock is getting faster, the orbit's shrinking. And the other one, he saw a concave up solution, which means the orbit's growing. So it turned around. And so we learn about how mass transfer, sort of the conservation of angular momentum and the interplay of the equation of state and GR can actually allow you to grow the orbits back out. Okay, there's another way you can use these to study how binaries change their orbital periods. They're probes of how dynamical channels influence the formation and evolution of close binaries. And what do I mean by that? What happens if you put something in a globular cluster? Are you able to preferentially form close binaries through stellar captures and encounters that would never happen out in the field? And so my scheme to figure this out was I got a JWST program approved to look at two of the densest globular clusters we know, actually the two densest, LILR1 and Terzon 5, and image them and basically take a movie and get light curves of them. When it actually got approved, I was a little terrified because I'd never worked with JWST or globulars before. A graduate student of mine is actually leading the analysis, but I'm going to show you some of the initial things I did with it. So these are the two clusters in optical images with a 4-meter class telescope. You might not be too impressed here. You see a little bit of fuzz for this one, and then like either this is the core of Omega Cen, which is not very dense, or like there's not a globular there. But if you go to the infrared, this is what they look like. So they're both highly obscured, which is a very good excuse to point JWST at them, by the way. But when I got this program approved, I was like, uh-oh, I'm in trouble. They look this bright. How is a 6.5-meter telescope going to cope with pointing at these? They're very interesting because they're full of X-ray sources and all sorts of other cool things. But I was very, very nervous when this data was taken. Like literally the night before, I was having nightmares that I was going to get saturated images the entire way through. So here's a drum roll. In 3 seconds, I'm going to show you the JW image. 3, 2, 1. So same field of view. That's what we spent $10 billion of taxpayer dollars on. So thank you, taxpayer. It takes very nice pictures. So you might go, where'd all the stars go? Like, there are a lot of stars here. It doesn't feel like there are many here. Don't worry. If you stretch the image, there's no shortage of stars. Your confusion noise limited all the way into the corners of the images. You have more stars than you do pixels in these systems. And so I immediately was like, I want to make light curves of this. But when I tried to do it, I had this annoying thing where the light curves would jump up and down. And it was every time JWST dithered, it would move them sources onto new pixels, which had slightly different responses. And this is a really extreme example of where you would just get all these systematics in the photometry. Normally, you want to measure this because it lets you put error bars on your JWST magnitudes. But like if you're trying to make a light curve, it's not good news. So even in light curves where I saw some variability, I was getting these jumps and was really disappointed. So I emailed the JWST people and said, like, look, I want to get rid of the dithers. They told me I was completely crazy, but I managed to convince them. So what I basically told them is just point it and don't move. Like, just don't move it, please. Even if all the APT warnings pop up, like, just listen. And it turned out that was a really, really productive way of doing it. So this is an image subtraction movie of that same globular. And if you look very closely, you'll see these little specks of black and white that flip color. Those are variable stars that are popping out of the subtracted images of this cluster. To give you an idea, this is a literal screen capture from DS9. I'm just zooming in on this corner of the image. This is what it looks like in the science image. Like when people saw these, they were like, good luck, Kevin, trying to get light curves out of that. There's an image subtraction movie of the same thing. So all the constant stars subtract out. and you just get the variable stars all over the place. There were thousands of these. And you could do it all the way into the core of the cluster. And the light curves are beautiful. Like these things look like what TESS does at 10th mag, but at 26th magnitude because JWST. And all sorts of different morphologies. This is a white dwarf being eclipsed by a main sequence star. This is some short period variable. And this one was my favorite. Someone sent me a paper right after I'd reduced this data on this source I'd never heard of called the rapid burster. It has like 1,000 papers on it. So it's some famous early X-ray source. And some group had claimed to have found the counterpart in HST data because they found a variable star. This is the thing circled in green. And they were like, you should check your JWST light curve of the counterpart. And I did, and I was like, it's an eclipsing binary. That doesn't feel like an X-ray binary. But then I noticed like the rapid burster is supposed to be here. This is actually a Chandra source. And so if I play this movie now, I was like, there's something there that's like doing some crazy flashy stuff that kind of looks like what I would call a rapid burster more so than this thing. So it turns out the counterpart is there and it's right on top of where it should be. So that was just something that kind of fell out of this data naturally, for example. There were 13 variable stars known in the field of the globular cluster TER5. I have about 1,000. There were 0 in Liller, so totally like game changer, I think, for studying globular clusters. And the exciting thing is JWST has this multi-object spectrograph called NIRSpec. But the thing about NIRSpec is you can open all these little micro shutters, but you need to know where to open them. So you need to know where your targets are ahead of time. Well, guess what? We know where all the targets are ahead of time. In fact, when you propose for it, they're like, you should get a JW image to check where your targets are. And it's like, don't worry, I've got that covered. So now we're going to get phase result spectroscopy of all of these if the TAC goes for it. And we'll be able to measure radial velocities and masses for all of these systems. I'll just say there's a whole group of students who formerly worked with me are doing the same thing with Hubble now in 47 Tuc and are also finding all sorts of cool stuff. Not able to hit the same photometric precision as JWST because there you can't do the no dither long stairs because it's in low Earth orbit, unfortunately. But it is powerful in the cores of some of these unobscured clusters. I'm going to skip the type 1a stuff because I have too many other exciting things to talk about. So pardon my skipping the slides. Oh, I'll just say the way we find these things is we actually data mine very large scale surveys. And I do like to show these slides. Since this is a Center for Computational Astrophysics, I should mention people are really worried about Rubin generating 10 to the 7 alerts per night. I don't work on alerts, I work on light curves, so that doesn't really faze me. That's 10 to the 7 alerts in 10 years. But a more interesting number to think about is it's really, if you add up all the images and all the pixels, it's about 10 to the 16 pixels in 10 years. And this number starts to get interesting for me because what I do is I use GPUs to data mine these data sets. And what I actually do is I do Fourier transforms on all of the sources in these data sets to very high frequencies to look for periodic signals. And so I actually calculate the number of floating point operations I do. It's more than 10 to the 21. So this is why we need GPUs to do this. But I was looking up Roman prefixes this morning and realized this is getting beyond my knowledge of them. I think it's like a yada flop or something. So anyway, there's a lot of computation that goes into discovering these objects. I'm going to skip this too. And I'll just say on the right, if you look at those black solid points with big error bars, that's all that was known as of 2018. And it took 40 years to discover those. The red shows you what I found in my PhD in 2 years. And the background there is my absolute most pessimistic projection of what Rubin's going to give us. It's going to be a lot. And let me show you why. So with ZTF, we were sensitive out to about this dashed green line. Rubin gets us out to the dashed blue line. That's a big difference in volume. And let me give you an idea of just how powerful Rubin is. This is a DSS image from about 20 years ago of the sky. So this is sort of the deepest all-sky image we had before the Sloan Digital Sky Survey. if you fast forward 15 years or so, the current state of the art came out around then, which is pan-SCARS, which is really our deepest northern hemisphere all-sky image. Now, if you co-add all of ZTF, you can go a little bit deeper because the sheer number of images it's taken. But this is currently kind of the best, deepest image we have in the optical of the whole sky. And you can see it's definitely better, right? We're getting deeper. This is, so you might say, okay, that's getting us this. How the heck is Rubin going to get us to that? So this is a Rubin image of the same field. Like, this is a game changer. Like, the step is so much larger than any previous step here.
And that's not even a coad, right?
I think this is actually a coad.
A coad, but not.
Yeah, not the full 10-year stack. Yeah. Like, game changer. So very exciting time to be in this business. I just want to give a shout out to Roman too. So our deepest all sky infrared image is 2MASS in the near infrared. The best I can do to mimic Roman is just show you a Hubble image. This is a Hubble image of that same field. So that's what's about to happen to our infrared sky map. This is an amazing time to be in astronomy. Just the leaps with these two surveys are so enormous compared to anything we've ever had. It's not just another incremental factor of 2 or something. Okay, and I'm running way too late on time, so I'm going to jump through. I'm going to skip the X-ray stuff. I just don't have time. I'm going to skip all this too, and I'm just going to jump to talking about CMOSs because I can't resist. So you saw, I really like this light curve. I really like light curves. All the slides I skipped had more light curves in them. I was very sad when I got to MIT and I couldn't take light curves with the Magellan telescopes. I was like, I have access to these amazing telescopes and I can't get the type of data I want. And I got tired about 2 years into my postdoc and I said, I'm going to figure out a way to do this. And it was a really opportune time because there's these types of cameras called CMOS sensors that have been skyrocketing in their sensitivity and quality as a result of the consumer cell phone market. So it's the same kind of camera as on your phone. And think about what the camera on your phone can do that your typical astronomy camera, like JWST sensors or the best spectrographs we have based on CCDs, can't do. Well, none of those cameras can do the 60 hertz at 4K resolution your phone can, right? And the other thing that's really special about your phone is, believe it or not, the noise associated with reading out an image is actually better than all of those cameras. And the reason is phones are really, really photon starved. And so to get good quality nighttime images or videos, they had to make the sensors really, really quiet to deal with low light imaging. And there's this really revolutionary camera released by Hamamatsu called the QCMOS 2 years ago, where that noise got down to about 1/3 of an electron. I'm going to explain in a moment what that means. Ignore this plot for now. I got this camera a couple of years ago and just plugged it into USB on my computer and started playing with it. And I took some data and saw this. So the highest noise pixels on that camera at about 1 electron of read noise, you see a distribution of signal if you just point it at some source of light. But if you look at the typical pixels, which are much lower noise, all these troughs appear. And it's like, what's that? What that is your noise is actually so much smaller than the level of signal associated with individual photons that you're resolving the signal level between 1 and 2 and 3 and 4 photons. And at that point, you can just tell it to round to the nearest photon and basically completely suppress your noise. So we're very excited about this thing. I took it out to a 14-inch in the middle of Massachusetts to do some first light testing with some graduate students. We got some beautiful pictures. The moon was like my favorite thing to look at that night. I then got motivated and started programming it in my office. This is a GPS antenna, PCI card to drop the data off. And then we took it, well, first I had to take it outside to make sure we could get GPS satellites. So I had to literally cart my computer out onto MIT campus. And then we took it back out to Wallace, this time on the 0.5 meter. And we got some data of an eclipsing double white dwarf. This is a primary eclipse and a secondary one. And I was blown away. And you might go, Kevin, you just showed us like the most beautiful light curves ever. Like, you're blown away by this, really? This is a 19th magnitude object. We were taking 1 second exposures. This is binned up, of course. In Massachusetts with 3 arc-second seeing on a ½ meter and a ton of light pollution. I was not expecting to see this. We saw the secondary eclipse. I was like, no way. And part of it is the seeing was better for us because we were imaging fast, and that lets you image faster than the atmospheric turbulence. So then I called up friends at Caltech and said, can I put this on my favorite telescope, the Hale telescope, which is 5 meter at Palomar. I love that telescope so much, I took a whole crew from MIT up there to go visit it. You may have seen this article in the New York Times about the dining ending at Palomar. That was the last big meal at Palomar. We were actually that group. And so this is a really special telescope because so the mirror is at the bottom here. It's a 5 meter. And it has a prime focus cage up at the top, where normally a big telescope would just put a mirror there and send the light back down to another focus. But the Hale's special in that you can actually put stuff up there directly looking down at the primary. And that's exactly what I did. So this was me installing the camera up at prime focus of the Hale, like 20-something meters above the primary. To give you an idea of how compact the setup is, this is just an air-cooled camera. This is a normal cryogenically cooled instrument for comparison. Very compact and easy to use. So this is a light curve I had gotten during my PhD of a double white dwarf with the Hale using an EM-CCD, so an electron multiplying CCD. This is an hour of data binned up with 5-second exposures. This is an hour of data with the CMOS. Same telescope, same filter, same seeing, 1 second exposures binned up. So it's a huge leap forward. This was a light curve of the Crab pulsar that they had taken with that EM-CCD, sampling at about 100 hertz. The period there is about 30 hertz. This is about an hour of data binned up. Here's a few minutes of data with the CMOS, sampling at 1,000 hertz. So I showed people that, and everyone was like, oh my God, we need to put this on Magellan now. And so then we actually started building a proper mount for it on Magellan. And within about a month, cobbled something together using commercial optics. And so this was kind of the whole group getting ready for it to ship down. We packed it up in a gigantic crate. I learned about shipping really heavy things. It was a lot cheaper than I thought. It was like 8,000 bucks. And I'm like, I've paid like 200 bucks to ship much smaller packages than this. Then it got to Chile. So this is the clay telescope that we were going to put it on. I took this really cool picture of just like clouds that flowed in the mountains, and we were way above the cloud line. And that's us getting ready to install it, and it mounted on the clay telescope. And this was our first light image of it. Fortunately, we had really nice control software because I'd been working with ChatGPT for like 2 years on making a really beautiful GUI for it. This is our first image. It was just Saturn. We took a vote. We like looked up what was up, and we were like, what should we point at first? And like everyone voted for Saturn. It turns out that that's the most popular astronomical target. Here's an eclipsing double white dwarf, so one of my sort of babies that I've been following for many years that we did a timing measurement of. This is perhaps some of the most impressive stuff. So I had shown you the Crab pulsar before. So Roger Ramani is one of the co-PIs on this, and he really likes pulsars. And he was like, I want to do this pulsar in the LMC. And I was like, okay, how bright is it, Roger? The Crab is 16th. And he was like, it's 23rd mag. And I was like, okay. And I was like, how fast do we need to go? And he said, well, the period is 50 milliseconds. And I was like, okay, let's try 25 milliseconds or 20 and just barely sample it. And he was like, no, I want like 2.5 milliseconds. And I was like, I did the math and I was like, you realize that's 1 photon every 50 images we take, right? And like, we have 75 pixels in the aperture because we're oversampling the PSF. And he was like, let's just do it. This is the best light curve that existed of it before. It's a couple hours of data taken with a PMT, a photomultiplier tube on a 4 meter. This is a few minutes of our data on it. So 23rd Mach, no problem. This is a millisecond pulsar, 2.5 millisecond period that we were sampling with 0.7 second exposures. And then I'll jump to my favorite slides now. This movie never plays, but I want to acknowledge there's a graduate student, Vera Berger, who works with Aaron Kara and I on black hole X-ray binaries. And one of the interesting targets we had here is we wanted to look at an accreting black hole, like a stellar mass one, and just see what it did. And a pretty famous one called GX339 happened to be going into outburst, because it always goes into outburst, apparently. And so we took a very fast light curve of it at about 100 hertz. And I saw these spikes where like it got brighter by a factor of 7. And I was like, is our camera having some issues now with like dark current events or something? So this is an image of it at 10 millisecond exposure. The black hole's there. This is the next frame. So it did brighten by a factor of 7. I checked, the other stars were not doing that in the field. This was not a fluke, and it did it many times. That's the next frame. So up and right back down. So this was kind of a spectacular form of data we got during that first commissioning run. I could not have asked for a more productive, like, first 3-day test run of this thing on the telescope. So we're going to be going down next month to do lots more with it. Long-term plan is to build a 6-channel instrument now, where we do simultaneous light curves in UGRIZ, and then an infrared arm as well. And we also have full Stokes polarimetry for people who are excited about that sort of thing. So if you're ever using Magellan, like I'm working on turning this into a facility instrument, so hopefully the wider community will be able to use it. Okay, now with the, and also mention bigger telescopes like GMT, you could imagine putting stuff like this behind them and what you could do with it. So that's also in the cards for the future. This is how much deeper you get in a GMT image compared to what we're doing on Magellan right now. Give you an idea of how powerful that is. 10 years of Rubin data of such a binary here binned up gives you a light curve like that. This is 15 minutes with one of those cameras on GMT at the same distance. So amazing follow-up facility potentially. Okay, so now I'm going to talk about this last section, which is related to how do stellar mass black holes form. Yeah, I'm very close to the end. Okay, let's just jump into it. So 2 of my best friends in this business are Aaron Kara and Kareem El-Badri. They both work on black holes. I've been on a lot of papers with the word black hole in them. I've been on a lot of different proposals with the word black holes in them. So I used to only do white dwarfs. They've converted me to the dark side, especially Aaron. And so if the clicker works. Oh, it's that movie that doesn't play. So I was very interested in high-speed imaging of these. So this was before I got that camera, and I was like, Aaron, I wonder if we look at a black hole really fast in quiescence, whether we could see it flaring fast and discover them that way. And I was like, has anyone ever tried this on a quiescent black hole? And there was this one I'd never heard of called V44 Cygni, where they had tried this with 5-second exposures. And I was like, oh, that's cool. Let me go look at a picture of it. So this is what I like to call Google Maps for astronomers, Aladdin. This is a DSS image of it. And then I switched it to a more modern survey pan-stars. And I was like, huh, there's another star like right on top of it. That's weird. And then I turned on the little Gaia boxes and I was like, okay, proper motion was -5, -7 point something. I clicked on the other one and I was like, huh, that's like exactly the same. That's weird. And so I went out to Simbad and Control F through the 1,200 papers on this and typed triple. And I found one paper that was like, it's really weird. We don't know how to form these X-ray binary things. Hierarchical triples would make a lot of sense. So I messaged Erin, like, did you know that this was in a triple? Because I can't find anything in all the papers. And she was like, interesting, I didn't know that. I messaged Kareem and he was like, huh, that's funny. I found this paper that says they should probably form in that. I was like, yes, my Control F search also turned up this paper. So yeah, it turns out the most well-known black hole X-ray binary was a triple staring us all in the face with really obvious Gaia data that was just sitting out there for 3 years and no one was bothering to check the astrometry. Let me tell you why it's exciting as I wrap up the talk. The tertiary is really far separated, so 3,500 AU away from the X-ray binary, which means it's barely bound. It's orbiting around every 70,000 years. The interbinary is a 6.5-day period. The tertiary happens to be going up the giant branch, which is really nice because stars don't really show their age that well until they start evolving up the giant branch. So we have a good age for the first time of a black hole low mass X-ray binary. It's about 4 gigayears old. But the really important thing that I'll end on is just saying the tertiary is so far out that it's barely bound. And what that means is when you form that black hole, you have to be very careful not to kick the inner binary, or you're going to disrupt it and lose that tertiary. And I simulated and I simulated. And what I found is the easiest way to explain the formation of the system is direct collapse formation of that black hole. And conveniently, I found this right around when Kishale found his disappearing star in M31, and we were like on the same wavelength that week. We were like, black holes form, at least some form from direct collapse. We're searching for more now. This is an image of a very well-known black hole where the proper motions here agree pretty well, but we're still off by 20 sigma because the error bars are so small. I looked at a Hubble image and was like, oh, this is an unresolved binary, and that could exactly account for that. I think this might be the first black hole quadruple. And now we're undertaking a campaign with both Hubble and hopefully eventually AO systems on big telescopes to find more close unresolved systems. I've gotten Aaron, who's an X-ray astronomer, to actually do optical observing with me to try to find more of these. I know I'm over time, so I'm going to wrap up there and say, like, there are lots of interesting questions I'm interested in with binaries, and I like building cool tools to observe them. Thank you.
Terrific. We have some time for some questions before we go to the reception. Will.
Coming back to the tidal dissipation that you were trying to estimate from the temperature of that secondary, the discrepancy is like several orders of magnitude, maybe 3.
Yeah.
Can you measure like a phase lag in the bulge? That's way too small, right, to get an estimate of the tidal dissipation rate. Is there some other way you can come at this? You know, the system is just way less dissipative than you expected.
Yeah, so one thing we think might actually be happening is that the tides only kicked in recently because they only become effective as it shrinks to a pretty short orbit and the coupling goes up. And my best theory is we know the tides are there because the orbit's decaying faster, so there must be dissipation. The best model we have is the dissipation's happening in the core rather than the envelope, which is what most of the models predict, and that there's just not enough time for that to diffuse up. Yeah, because here the merger time scale is 100,000 years.
Yeah, okay.
Yeah, so that's our best idea right now, because the orbital decay suggests that tides are definitely doing something. Yeah.
Okay, cool.
Next question. We'll go back there and then Barry.
Well, a very simple question. After you can resolving the millisecond pulsar very well, does it helpful for the PTA stuff, like pulsar timing array? I mean,
That's an interesting question. Could we build optical pulsar timing arrays? I think the answer is probably not yet because there are so few millisecond pulsars that are bright enough in the optical to be detectable. But also not many have been observed because people haven't had cameras that go this fast until now. So it may be that as this observing mode becomes more common, that we'll pick up more of them. But for sure, you can use the timing solutions from them. The one caveat I should say is the optical light curves are often offset from the radio light curves by some amount. This has been seen in the crab. We actually detected it and had to correct for it. So you can't just mix signals from different wavelengths naively. You have to be very careful about keeping separate ephemerae for each of them.
Okay, Barry, and then I saw Adrian's hand up, and then I don't know if we're going to have time, Sabina. Do you think it would keep until the reception? Okay.
So tell people what you told me, the faintest thing that you can see if you get your JWC image of the center of our galaxy.
Yeah, I think we can get down to like 26 variability on the order of 26 magnitude. So normally you would be much shallower in the galactic center because confusion noise. So, I mean, to be clear, JWST is detecting like directly imaging brown dwarfs in 47 Tuc, right? So like it can see a brown dwarf, like something the size of Jupiter and like a couple thousand Kelvin at like 8 kiloparsecs. The problem is in the galactic center, you've got all these other things, but the key is with the image subtraction, you can get rid of a lot of the effects of the confusion noise that normally would hurt you with source detection and things like that.
I like that Vera just wanted you to share.
Yeah.
Adrian.
Yeah, I was sort of, well, let's see. So I was thinking of related things to like pulsar timing, but with stars. Since stars are also clocks, they pulsate, right? They're surfaces. And Andy also mentioned earlier, maybe he was talking to you about why not look at some stuff like traditional single stars and see what you get from this super high timing stuff. But is there any hope of doing making a PTA like array from surface pulsations of white dwarfs?
Yeah, so white dwarfs do weird things when they pulsate. They're not very good oscillators. That's the problem. Millisecond pulsars, at least if they're isolated and they don't glitch or something, are very, very stable clocks. Less so true for white dwarf pulsators.
What about tidally driven oscillations? Those are really narrow.
Yeah, maybe. Yeah, those might. I would say the other good clock is eclipses. Like every 7 minutes, you get a really sharp eclipse that you can time to milliseconds because of how sharp the ingress is. That's a bit, it's not stable in that, like, it is changing frequency, but we know how it's changing frequency to high precision. So I actually think the Lisa binaries may be one of the coolest new clocks we unlock. It's funny, you could use a gravitational wave source as a clock to do other frequency gravitational wave stuff.
Cool.